Okay, good afternoon. Welcome to the Cavity QED seminar series. And this seminar series is supported by the National Science Foundation. And we need to include participation statistics in our reporting. So please scan the QR code and record your attendance. So our project on Cavity QED is supported by the NSF National Science Foundation through their NRT program, NSF Research Traineeship Program in the area of QISE, Quantum Information Science and Engineering, entitled Broad Research in Interdisciplinary Development for Groundbreaking Engineering in Cavity QED. We have a long project name. Let's just call it CQED. So this is our team. So we have 9 faculty members as the core members, and we are electrical and computer engineers, material scientists, and the physicists, and one from chemical and biomolecular engineering. We also collaborate with various entities on campus, including CTE and AECP, CAPC, and D&I in various professional development and education activities. And this NRT program is managed within the Applied Physics Graduate Program, which is administered by the Smalley-Curl Institute, SCI. This is a new program, but we already have 6 NRT fellows. These are all APP graduate students, including some senior students, and also a new addition. He just joined us last week. So what we do in this program is Cavity QED. This is traditionally a subject of quantum optics and atomic, molecular, and optical physics. We study a quantum emitter, often a 2-level atom, placed in the middle of an optical cavity, which is a pair of highly reflective mirrors. And we study the interaction of such a quantum emitter with photons trapped inside the cavity. This kind of very simple system turns out to be a very useful platform for testing some of the fundamental concepts in quantum physics, such as superposition, entanglement, complementarity, and decoherence, as demonstrated by some of the pioneers in this field, Professors Harosh, Kimball, and our own Randy Hewlett, Professor Randy Hewlett in the physics department at Rice University. And this kind of system is becoming more and more important for quantum technology because this can be used for single photon generation, atom-photon entanglement, and quantum transaction. A few of the important elements in quantum technology. That's why we have a multidisciplinary team of researchers working on not only atomic and molecular systems, but also materials and devices. So we studied not only the physics of atomic and molecular and optical cavity QED, but we use various cutting-edge materials and artificial quantum structures. Some of the ongoing research topics include cavity design and engineering, device fabrication, materials design, growth and characterization, and all kinds of theory and experiments related to light-matter interactions inside optical cavities. So within this program, we cover a wide range of topics, from very fundamental topics to very applied research topics. Some of us are interested in studying phase transitions, the ground states and excited states of many body, many particle systems in condensed matter and AMO systems. Some of us are using Cavity QED platforms for simulating biological and chemical processes, including photosynthetic processes and catalytic processes. And some of us are using such Cavity QED platforms for quantum sensing. For example, biosensing using 2D materials. And on the very applied side, we're using Cavity QED systems for quantum information processing and network systems. So today, I will talk about some of the ongoing research within my group. So my group is an experimental optical spectroscopy group, and we're interested in studying many-body physics, so-called many-body cavity QED. This is at the interface between two traditional physics disciplines, quantum optics and condensed matter physics. So quantum optics deals with the quantum nature of photons, whereas condensed matter physics deals with interacting many-body systems. We combine the two. There are seats there. Yeah. Right. So we confine many particles interacting electrons or atoms or ions inside optical cavities, and we study their states and dynamics. So instead of an atom, right, we have a piece of material, and this material strongly couples with photons inside the cavity, and they hybridize. So light and material in this case, strongly hybridize to form the so-called polariton states. And the coupling, compared to atomic and molecular systems, solid state systems have various transitions and resonances with huge dipole moments or oscillator strengths. So this is because of the extended nature of the wave functions, in addition to the fact that there are many cooperating electrons. These two facts lead us to a new regime of light-matter interaction, strong. And this the nature of the light-matter interaction can be characterized by this term strong, but it can be very strong, super strong, ultra strong, deep strong, extremely strong, or ridiculously strong. All these have rather interesting definitions. Okay, so I will tell you some of these throughout this seminar. But yeah, strong, ultra strong, deep strong, super strong, very strong, etc. But the key factor or key quantity is G. Whenever G becomes larger than a certain quantity, certain energy scale in your system, you enter a new regime of light-matter interaction. So what is G? So G is it's a rate Okay, it's a frequency. It's expressed in hertz, or it has the same unit as omega. So h bar g is an energy, and that energy is given by the product of two parameters. One parameter representing the matter side, and the other parameter representing the cavity or photon side. So mu12 represents the dipole moment associated with this allowed transition in this quantum emitter, the two-level atom. And evac is the strength of the electric field of the vacuum electromagnetic field surrounding the atom. I'll come back to this point later, but it's just think that this is just an electric field, and the product of the two gives you the light matter coupling strength. So this immediately tells you that in order to increase G, you want to find a material that has a huge dipole moment, and you want to reduce the volume of the cavity. You want to confine photons and atoms in a small region of space, because the electric field is inversely proportional to the square root of the so-called mode volume. The smaller the cavity, the larger the electric field, and the larger the coupling strength. Furthermore, the coupling strength G can be increased by having an ensemble of particles, a collection of identical particles, as shown by Dickey in 1954 originally. So the so-called Dickey cooperativity states that if you have n identical dipoles or two-level atoms in a small region of space, smaller than the wavelength corresponding to the two-level spacing, such a collection of atoms behaves as a single atom with a giant dipole moment. And this enhancement is mathematically given in this form. So when you have an n atoms, compared to the single atom case, the coupling strength is enhanced in proportion to the square root of the number of atoms, n. So condensed matter systems have an inherent advantage compared to atomic and molecular systems because of the existence of huge numbers of particles in condensed matter systems. So in order to do anything interesting in cavity QED systems, first you have to be in the strong coupling regime, where G is the largest rate in the system. G is higher than any other dynamical rates in the system, which means the light matter coupling dominates the dynamics of the system. So G has to compete with various types of decay rates, decay processes that destroy the coherence of photons and matter and the light matter interaction. So we use gamma to represent the matter decay rate, which is very, very fast in condensed matter systems. This is one huge disadvantage of using solid state systems compared to atomic systems. Atomic systems have very long lifetimes, coherence times, but in solid state systems there are all kinds of phase destroying scattering processes. So gamma is very high, okay, in solid state systems, but G can be made larger than gamma. And kappa represents the decay rate of photons. So this is the rate at which photons decaying out of the cavity. So this is related to, so 1 over kappa is the lifetime of photons that are trapped inside the cavity. And it's related to the Q factor. So the Q factor is inversely proportional to kappa. So by minimizing kappa and gamma, G dominates. So G determines the dynamics of the system, and the the main coherent dynamics one can see in such a system in the strong coupling regime is Rabi oscillations in the time domain. So these oscillations represent the coherent energy exchange process inside the cavity, between the cavity and the matter. So that the number of photons and the population of atoms in the excited state, they exchange their populations, right, coherently. And one cycle is called the Rabi cycle. It's 2 pi over g. So 2 pi over g is a period, right, time period of one such coherent process of energy exchange. And the envelope of such coherent oscillations is decreasing. This is determined by a combination of kappa and gamma. And if this is what's happening in the time domain, if you Fourier transform this into the frequency domain, you see 2 peaks. This is interesting because originally you had one atomic resonance transition, but inside the cavity, in the strong coupling regime, now you have 2 peaks. And these are often called polariton splitting or Rabi splitting. And this UP represents the upper polariton, and LP represents the lower polariton. And the splitting between the two is given by 2G. So the larger the G, the larger the Rabi splitting, and the line width of each polariton peak is given by the average of kappa and gamma. So this kind of situation actually arises at the so-called zero detuning situation, where the bare cavity frequency and the bare atomic transition are equal to each other. But experimentally, we have this additional parameter called detuning, which is the difference between the two, right? Without any coupling, we have bare frequencies. We typically tune the matter frequency. So we fixed the cavity frequency, but the matter frequency can be tuned through temperature or magnetic field, electric field, or pressure. So in the case of a magnetic resonance, by changing the applied magnetic field, we can change the cyclotron frequency or Zeeman frequency that can go into and out of resonance. And once you do this experimentally, what you see is anti-crossing. And anti-crossing is the hallmark of polaritons, as demonstrated by Elijah, a beautiful dancer. So large detuning. Yeah. So here, small detuning, you have maximum hybridization between light and matter. At the exact zero detuning, you have 50% light, 50% matter. But when you move away from the zero detuning point, this becomes more and more matter. So here, it's almost purely matter-like. But then if you move this way, this is more photon-like, right? So the ratio between the two changes as a function of detuning. So the Rabi splitting depends on, first of all, the coupling. So the Rabi splitting here, capital omega, first depends on the light matter coupling rate, G, and the detuning, as we just saw. But also, it depends on one additional parameter, n. So this n here in this expression represents the number of photons. The more photons you have, the larger the Rabi splitting. So that's interesting. If you drive it by putting more and more photons, of course, the light matter coupling becomes stronger. But we are more interested in the other extreme, where we reduce the number of photons gradually to the ultimate limit of n equals 0, where there are no photons inside on average. But as you see from this expression, even when n equals 0, you get a finite expression, finite quantity 2G. This is the vacuum Rabi splitting. And what's happening, so if the cavity is empty, if there are no photons, what is the matter coupled with? The matter is coupled with virtual photons. The quantum vacuum is not empty. It's filled with virtual bosonic excitations, especially photons, that come into and out of existence, corresponding to the fluctuating electromagnetic fields with 0-point energy 1/2 times h bar omega. And a spectral energy density which is proportional to the cube of omega. There's a continuous photonic density of states in this free space vacuum, as noted by some of the pioneers of quantum mechanics. And in fact, such 0-point fluctuating quantum vacuum fields are responsible for some of the most profound physical processes in nature, including spontaneous emission, the Casimir force, the Unruh-Davis effect, the Lamb shift, van der Waals forces, electrons' anomalous magnetic moment, etc. In the current context, the most relevant process here is spontaneous emission. So let's spend some time on this very elementary and important process in light matter interaction, the so-called Purcell effect. This is the first most important effect known in the context of cavity QED. And all you do is to place an excited two-level atom inside a cavity. And you tune the cavity distance in such a way that one of the photonic modes will coincide in frequency with the transition frequency of this two-level atom. Under such a condition, the spontaneous emission rate is increased. So spontaneous emission is accelerated. What's happening? Right? Spontaneous emission can be viewed as stimulated emission, stimulated by the fluctuating quantum vacuum electromagnetic fields surrounding such an excited atom. What the cavity does is when you have a cavity, when you have two metallic mirrors, they introduce new boundary conditions for the quantum vacuum fields to satisfy that changes the local photonic density of states surrounding the atom. More specifically, in free space, we have a continuum of photonic density of states. But inside a cavity, you have a series of peaks in the photonic density of states. If one of them coincides with the transition of the spontaneous emission, then the rate is enhanced because the number of available photons or virtual photons increases at that transition frequency. That's why if you look at the excited state population as a function of time, if inside a cavity, it decays faster. So this is the Purcell effect. There's an opposite effect called the Hewlett effect, discovered by Randy Hewlett when he was a graduate student at MIT. And he was able to inhibit spontaneous emission. This is really the opposite of what I just said about the Purcell effect. Basically, you're eliminating available photonic density of states at the transition energy. In that case, this excited atom stays here forever because there's no stimulation. So no spontaneous emission, it's prohibited. So these two, I spent some time on these two effects because these two effects really motivate us condensed matter physicists. So because all you did here was to place an atom inside a cavity. You didn't drive the system, right? Everything you did was just to place the atom inside the cavity. Can we do something similar in the case of condensed matter systems or solids? Just by placing this cavity inside the cavity, can we induce any change in material properties? So you do some measurements inside or outside the cavity in free space, and then you perform exactly the same measurements inside the cavity. Will anything change? For example, can we modify electrical conductivity, which would correspond to lightless photoconductivity? Can we increase the transition temperature of a superconductor? Can we modify the topology of an electronic band? Can we create or destroy phases of matter just by placing it in a cavity? So these are the questions that people in this field are asking. And there are many theory papers. So the theorists are well ahead of us experimentalists. And there are many interesting and predictions for exotic effects related to superconductivity, magnetism, new phases of matter, ferroelectric states, etc., induced by cavity fields in the dark, inside dark cavities without any external driving. But some of these, or most of these phenomena can be achieved experimentally only in the so-called ultra-strong or deep strong coupling regimes. And the definitions are shown here. So the ultra-strong coupling regime arises when G becomes a significant fraction of the bare resonance frequency omega naught. And the deep strong coupling regime arises when G becomes larger than the resonance frequency omega naught. So we use this dimensionless parameter eta to represent the strength of light matter coupling or reduced light matter coupling strength. So physically speaking, this is a very unusual regime, because usually you have two oscillators, light and matter. They are oscillating at the bare frequencies of omega naught. And typically, Rabi oscillations occur on a much slower time scale. So the Rabi oscillations are typically slow. It's a slow process compared to the original oscillation frequencies. But these regimes occur when the Rabi oscillations become faster and faster, and eventually become comparable to the original oscillator frequencies, which means even within the first optical cycle of the bare frequencies, and light and matter are already exchanging energy. So we completely lose the original identities of light and matter. They are totally hybridized. And experimentally speaking, and historically speaking, when the field of cavity QED started in the 1990s in France and Caltech, in Paris and Caltech, all these, if you plot this particular parameter, right, reduced light matter coupling rate, this parameter was 10 to the minus 8 to 10 to the minus 6. Interesting, they were still in the strong coupling regime. They were able to see vacuum Rabi splitting because atomic transitions are so narrow, right? So the coupling is weak, but the lines are so narrow. So they were still in this strong coupling regime, but they were far away from the interesting regimes of light matter interaction. Even nowadays, if you're using atomic and molecular systems, this parameter remains very small. But around the same time, solid state cavity QED started in the systems of exciton polaritons, microcavity exciton polaritons, by Westbrook and Arakawa. So they, from the very beginning, it was already 10 to the minus 3 in solid state cavity QED. And then over the years, various types of condensed matter solid state systems have been used for cavity QED studies, and many of them are now in this very interesting USC and DSC regimes. This is one of our earlier experimental demonstrations of USC back in 2018 in the so-called terahertz frequency range. Right? So one terahertz is 10 to the 12th hertz in the 300 micron wavelength range. So this is the so-called Landau polaritons. So we have a two-dimensional electron gas in a perpendicular magnetic field which quantizes the electronic motion and placed inside a cavity. And when the cyclotron frequency becomes equal to the cavity frequency, zero detuning occurs. So this is where the vacuum Rabi frequency occurs. This is 2G. And thanks to the large Q factor and the ultra-high mobility of the two-dimensional electron gas in this system, the line width is very, very small. So that's why we're able to achieve a huge value of so-called cooperativity. This is comparing light matter coupling and the decay rates. So we're definitely in the strong coupling regime, over 3,500. And furthermore, if you compare the Rabi splitting divided by 2 and the cavity frequency, this was 36%. So we are definitely in the ultra strong coupling regime. More recently, using certain phonon polaritons in a soft material, lead telluride, there's a terahertz phonon, a TO phonon with a large oscillator strength, and we coupled it with a meta surface like cavity structure, and we were able to achieve 1.25 for the reduced coupling strength. This is in the deep strong coupling regime. So we're studying various types of polaritons, including Landau polaritons, exciton polaritons, Zeeman polaritons, magnon polaritons, phonon polaritons. These are traditional polaritons in the sense that they all include photons. But we also have exotic types of polaritons without explicitly including photons. Instead, we are using other types of bosons. In this case, we are coupling spins with magnons. So magnons instead of photons. And we are also coupling magnons on magnons, boson-boson coupling. Here we also have plasmon-plasmon coupling, another type of boson-boson coupling. In all these systems, these are all experimental studies, we have been able to go into the interesting USC and DSC regime. And there's one specific phase or process that we are trying to achieve. And this is the so-called super radiant dream, or the super radiant phase transition. So let me focus on this topic in the rest of this seminar. So let's start with this situation. You are already in the ultra-strong coupling regime. So the G is comparable to omega naught, but G is still smaller than omega naught. So specifically, using our simple formulas, we know that the frequency of the lower polariton is omega naught minus G. Right? So this is omega naught minus G, this is omega naught plus G. But if we increase G further, G can become equal to omega naught. When this is achieved, the frequency of the lower polariton becomes 0 because omega naught minus G is 0 because omega G is equal to omega naught. And if you further increase this, then the frequency of the lower polariton is predicted to become negative, which is unphysical. This means that first of all, this simple treatment breaks down, the simple theory breaks down. There is some sort of interesting instability happening in this frequency, in this coupling strength range. So this was first noted by Hepp and Lieb in 1973. And they used a so-called Dickey Hamiltonian, which describes a system of a single mode cavity containing n dipoles, n two-level atoms. And then they constructed this phase diagram as a function of temperature normalized by the cavity photon energy and the coupling strength, normalized coupling strength. And they found that at low enough temperatures and high enough coupling strength, there's a new phase, there's a new ground state, which is different from the normal ground state. What happens in this ground state? In this new ground state, once you enter this new ground state, two so-called order parameters become finite. These are the atomic inversion and the photon number. Atomic inversion tells you the fraction of atoms in the n atoms that are in the upper state. I forgot to say. So I'm focusing on the t equals 0 situation, right? So this phase transition occurs even at t equals 0. If you stay at t equals 0 and if you just tune this, you go from this state, this phase into this state, this phase. This kind of phase transition is called a quantum phase transition because the phase transition is not driven thermally. This is driven by quantum fluctuations at t equals 0. So at t equals 0, right, ordinarily you would think that all the atoms are in the ground state. These are two-level atoms. But once you enter this phase, then some of the atoms are in the excited state. Furthermore, the number of photons, again, we started with the assumption that there are no photons. We're interested in that regime, dark cavity with no photons. But once you enter this interesting phase, the number of photons becomes finite, right? So these two order parameters become finite once you enter this exotic quantum phase. However, only 2 years after the original paper by Hepp and Lieb, this paper was published, the so-called no-go theorem. So these theorists from Poland claim that the recently discovered phase transition by Hepp and Lieb is due entirely to the absence of the a squared terms from the interaction Hamiltonian. What does this mean? So when you have a free particle, a free atom, and when you introduce electromagnetic fields, so cavity electromagnetic fields, what you do is you add a new momentum introduced through the vector potential A. So the vector potential representing the electromagnetic field is added to P. P becomes P plus EA. And if you expand this, you have the original kinetic energy and the main light matter interaction. This is A dot P. This is the usual dipole-based, electric dipole-based light matter interaction. And usually you stop here but there's a third term proportional to the A square of the vector potential. This is usually negligible in linear optics or ordinary nonlinear optics. But once you are in extreme or non-perturbative nonlinear optics regimes, and especially in ultra-strong coupling regime in cavity QED, you cannot ignore this. And if you add this term, if you retain this A squared term, sometimes called diamagnetic term also this, if you retain this diamagnetic term, you find that the frequency of the lower polariton will never become zero. It never crosses zero. It stays positive. It asymptotically approaches zero as you keep increasing light matter coupling. So this figure tells you that there's no phase transition. That's why it's called no-go theorem for the superradiant phase transition. And this was supposed to be the end of the discussion, but it turned out to be the beginning of 50 years of continuing debates among various prominent theorists, starting from the 1970s and 2004, 2007, 2014, 2014, and as recently as 2018, 2019, 2019, 2020, 2022, 2022. This is 2025. This is one of the latest addition to this series of theoretical papers debating with each other, pointing out some of the approximations they made, and some of the fact that the gauge invariance is broken if you're not careful in some of the treatments. And they summarize this area as a topic of considerable controversy, exasperated by conflicting no-go and counter no-go theorems. And we show that a ferroelectric phase transition can, in principle, still occur. So, yeah, I have a few minutes. No, 5 minutes? 8 minutes. Okay. Yes. So yeah, I don't have to go through all these. So I have various topics to discuss, specific experimental systems to discuss. All these are for realizing and observing the predicted superradiant phase. And the first deals with quantum Hall systems, two-dimensional electron gases in perpendicular magnetic fields, which Landau quantizes in cavity. I talked a little bit about this. The second system deals with electron spin resonance, spin precession, in addition, instead of the cyclotron motion, orbital motion. The third one is rather exotic, so maybe I should just talk about this. Magnetic superradiant phase transition. So first, the motivation why we started looking at magnetic systems was we were stimulated by this 1978 paper. So this paper is rather interesting and unique in the literature of the superradiant phase transition debate, in the sense that all the others, the theoretical papers deal with electric dipole light matter interactions. But only in this paper, they didn't prove anything, but they just said we cannot rule out phase transitions based on magnetic dipole interactions. So by going from the electric light matter interactions to magnetic light matter interactions, there may be a possibility to avoid the no-go theorem. So that was our original motivation to start working on magnetic systems. For example, if you look at this paper by Elijah, this latest paper, we talk much more about the motivation about using magnetic systems. But what I just want to finish, focus on in the remaining time is this most recent, one of our recent papers published by Da-Sung Kim, who recently graduated from the applied physics program. It's called Magnetic Superradiant Phase Transition in an Anti-Ferromagnet. So this project started quite some time ago when Shunwei Lee was a graduate student in my group. After that, he became a postdoc at Caltech, and now he's a faculty member at National University of Singapore. So we started looking at this material called erbium iron oxide. And this magnetic system has two subsystems, two magnetic subsystems consisting of ion spins and erbium spins. Both are magnetic. And ion spins order at a rather high temperature antiferromagnetically at 650 K. So below 650 K, the ion spins are ordered antiferromagnetically. And the erbium spins, on the other hand, are paramagnetic. They remain paramagnetic down to 4 Kelvin. So we have this, so yeah, two subsystems, and they respond to electromagnetic radiation in very different ways.